Okay. So where are we? We have finished Unit 4, unless you guys have questions, which it would be fair enough. And so we've done multiplexing and demultiplexing. Unit 1 was binary numbers and some beginning about resistors and current and so forth. Unit 2 was a truth table, sum of products, product of sums, resistor series and parallel. Unit 3 was Karnaugh maps and resistor networks. And Unit 4 was multiplexing and demultiplexing, and then we did sort of more resistor networks. So that's the material for test 1, which we have yet to schedule. It will be a 75-minute test. There will be, the first problem will be a resistor network. Harder than lab 3, not about the same or a little bit less than lab 4. You will have to do some part of simulate. It'll be mostly about you working through equations. These were in series, those were in parallel. And then you'll have to do at least one something about simulating, probably add the meters. So I probably won't have you simulate the entire circuit, but I'll probably have you add meters. That will be probably the first problem. And people who aren't coming in, you need a way. One, you need some access to the software. You will have to do some building, but you will not have to, sorry. And then, so you need some access to the software. And if you're going to write out your algebra for the resistor network, you will need some way to get that to me, to take a picture in your phone or what have you, some way for you to show me your work. I don't need to necessarily see values on a calculator. You can show me values on a calculator if that's how you want to show your work. But I need something where you say, like, here I've written down an equation that I'm trying to solve, or I just announced and I'm saying these two are in series and here's the result of them being in series. So I need some kind of work shown in terms of equations. And if you are writing that, that's perfectly fine. It doesn't have to be typed. It can be just written on a piece of paper, but you need a way to get that to me if you're not physically here to hand me that piece of paper. Okay. So that's the first problem on this test, will be a resistor network. Then and then the order, I don't know about the order after that, but I usually make that the first problem. It will be worth, because it'll be like, there'll be some in series and some in parallel, and then more in series and maybe more in parallel, and find the current, find the overall resistance, and find the current, and then maybe do a backward step or two and add some meters. Between all those things, it's going to be like 20 points or so. It's not oh, I can skip that problem and do fine on the test. If you skip that problem, you're down in the 70s to start with. Okay. There's going to be a sum of products. I'm going to give you a truth table with probably 3 inputs, and I'm going to say, tell me the sum of products expression, and I'll probably have you build that. But you don't have to build it from scratch. Only suckers will build it from scratch. There's the switches and the NOT gates, they're always the same. So why don't you have them built ahead of time, and then and the NOTs are there. You always know there are going to be some NOTs. And the only thing that changes is connecting to the AND gates, and that's about it. And then to the finally OR gate. But it can be 60–70% built before you even start. So building that from scratch would be, well, I'll say it's stupid, but a bunch of people probably will do it. So build it ahead of time. And I will also give you a product of sums. So you're expecting a resistor network for sure. You're expecting a product of sums. You're expecting a sum of products. You're expecting a Karnaugh map. Probably won't have you build a Karnaugh map. I'll just probably ask you to simplify. On the network, I'm probably asking you to add meters, voltmeters in parallel and meters in series. What else will be on this test? And a Karnaugh map. There'll be some binary number things. You're allowed to use the calculator. I don't expect you to sit down by hand and multiply by 2 or divide by 2 repeatedly to get these answers. I expect you to use the calculator. The timing of the test is expecting you to use the calculator. So if you want to grind out the algorithm by multiplying by 2 or dividing by 2 over and over again, that's on you. That's not what I want you to do. That's not what I expect you to do. That's not how the test is designed. But other people have you do that in other courses, so it gets, that ability gets tested somewhere else. I'm not interested in that. So I'm interested in aspects of it being finite. So I'm interested in, there's almost always on my first test some kind of question like, if I have this many bits, how many combinations can I have? There's always some kind of question of that order. There'd just be, here's a binary string, interpret it. Here are, what's the largest number? What's the largest signed number? What's the largest unsigned number? Right? Express this fraction as a binary fixed point number. All those sort of things in the binary thing, you're expecting that. Resistor network, Karnaugh, and then something with multiplexers and demultiplexers. That is not, I can't really do much in terms of modifying those circuits. It's, do you understand how they work? A multiplexer is a multiplexer, a demultiplexer is a demultiplexer. It was, what can I, and then I will ask some questions about them. I will have some paragraph with, a blank, and you'll have to fill in the blank. And you'll have to say, oh, it's a multiplexer, it's a demultiplexer, or it's just some kind of fill in the blank. There'll be some question from the book. Maybe 2 questions from the book. Sometimes I'll give you like a fill in the blank from the book, and other times there's usually some that'll write a couple of sentences for me. And basically, you're allowed to access the book, you're allowed to access your labs, you're allowed to access your homeworks. So I'm just trying to catch out the people who haven't bothered to read the book at all. But it shouldn't be hard. If you're somewhere in the ballpark and it makes it sound like you read the book, I'm happy. All right, any questions about what's on the test or any questions about that material? Anything you want, any additional examples you want me to do?
Can you show what a decoder looks like?
The decoder, okay. So I made a demux for you. So I'm going to open that up. Okay, so here was my demultiplexer. I'm going to save it as and make a decoder. And I'm going to take away the data. That's the big difference between a demultiplexer and a decoder, is there's no data input. I'm going to take away all of these. Okay, and then these should be 2 input AND gates now. So I'm going to do a replace and make it AND 2. I'm going to do right click properties, replace, AND 2. Properties, replace, AND 2, one more. Properties, replace, AND 2. Okay. When you take this, and yeah, so I should say, and that's the decoder. It's enter some address, enter some select input, and then you pick something. It's not clear in this picture what you're picking. I might be picking a register, or I might be picking something else, but the decoder is the picking. So one of these guys gets selected from the others. So right now I'm in high, so I'm picking the last one, the third, the one at address 3. So before there was some data that determined what got through, but now it's just the act of picking. I'm picking of 0, 1, 2, 3. I am currently picking 3. So that is a decoder. So I'm not going to give it to you, but you watch back the video and build your own. And that was one of the things on lab 4B, I think. When you take the test, you are going to paste pictures of your circuit into your Word document, and you are also going to sort of save everything in a folder and zip that up and send it to me. If your circuits are sort of nice and organized, I'll be able to look at it and see if it's right. And I'll just work from the Word document. But if it's, I always have like this line goes all the way down, and the knot goes all the way down, and this line goes all the way down, and after the knot goes all the way down. I try to keep it always this sort of style, and always have my AND gates coming out at sort of right angles to these NOT gates. That for me helps me stay organized and makes it easy for me to see. You don't have to do it that way. You just have to connect it correctly. But you do have to save your circuit and submit it as part of your test. So then if your circuit's kind of messy, but it's correct, then I'm going to test your circuit by operating it. I'd rather test your circuit by just looking at it. But if I need to, I will open up your circuit and run it to make sure that I'm not taking away points if you've got it right. So it's usually as a backup, but you want that backup. So the main thing is the Word document. That's mainly what I grade, but I ask for the files in case I need to test what you have, in case I'm having trouble finding. Sometimes the wires get on top of one another and it's hard to see what's what. Then I'm going to go by the operation of the circuit. Okay, so that's the decoder from lab 4B. Any other questions? Things you want me to do another example of, or anything like that, or something you want explained again? Don't forget all those binary number things, 2's complement, 16's complement. How do I interpret the number as a signed number? How do I interpret the binary string as a signed number? How do I interpret it as an unsigned number? Do we have any questions, anything you want me to review? Okay, then I will move on to Unit 5, which is not on the test. Okay. So far I have in the in Unit 5, I just have links to the pre-recorded stuff. I don't have, I'll post up the lab portion this evening if I remember. Post unit 5, okay. All right. So the topic we're moving into is an adder to build some circuitry that does addition. And we're still in, this will be material not on test 1, but on test 2. But the material is still similar in that addition just depends on inputs. You will have numbers that you want to put in, and based on those inputs, you will get some output. But the input will always depend on the same output. It does not depend on memory or on the state of things. So if you've read the book, he talks about a thing called a finite state machine. So that depends on both inputs and the state of things. Addition's not like that. So addition is still basically a truth table. So let me open up, say, a Word document, and I can start to draw some things. Okay. So let's say I want to add, we've seen this before when we talked about binary numbers. We mentioned addition. We didn't worry about performing the addition electronically. We might have talked about doing the addition ourselves, but we didn't talk about it figuring out the logic of addition. But let's figure out the logic of addition. That should be enough. Okay. So I'm going to add some binary numbers. 1, 2, 3, 4, 5, 6, 7. Let me have one more column. Okay. So I'm going to add 2 8-bit numbers. So I'm going to say it's a 0, 0, 1, 1, 0, 1, 0, 1. I'm just making something up, doesn't matter. That's a number, and I'm going to add it to 0, 0, 0, 1, 1, 1, 1, 1. There. So I'm adding those 2 numbers. And this is, I wanted another row. So this is, we have a positional weighting. And so this is the 1's place, the 2's place, the 4's place, the 8's place, and so on. And so I'm adding 2 8-bit numbers, and I'm getting an answer. So I'm going to put the answer down here. God, leave me alone. So in binary numbers, you add 1 and 1. 1 and 1 is 2, but in binary 2 is in this 1's place is a 0, and then you carry a 1. So this is number, I'll call it number A. This is number B. These are my carries. This is my, I'll call it my places. And this is my sum. This is my answer. Okay, so I went to the 1's place. I added 1 and 1. I got 2, but that was a 0 in the 1's place. And I carry a 1 over to the 2's place. And then I add 1 and 0 and 1. And I get 2. 1 and 0 and 1 is 2, which is 0 in this place, in the 2's place. And I carry a 1 over to the 1's place. And then I have 1 and 1 and 1, which is 3. And that is a 1 in that place, 1 in this place, and carried a 1 over here. That is 1 and 0. That's a 2. So there's a 0 here. That's an O. That's a 0 and a carry of a 1. And 1, 2, 3, so that's a 1 here and carry. 1 and 1 is, and 0 is 2. That's a 0 with a 1. 1 and 0 is 1. And no carry. Well, there were too many carries there. 0, 0, and 0 is 0. Okay. So now, so that is addition. We've seen that before. We played games with addition before. We define negative numbers based on addition. So we played this game before, 16, 32, 64, 128. I'm too lazy. All right. So now what we want to do is we want to focus on one position, one of the positions, say the 8th place, the 4th place, doesn't matter. One of the positions, and we want to determine the logic of addition for one position. Logic of addition for one position. For example, the 4th place. It doesn't matter, but I'll just say, for example, 4th place. Okay. Now, when we make a truth table, when we're doing logic, we want to write out a truth table. I said it was just based, it's not a finite state thing. It does not depend on the state of things. It just matters the inputs. So in the 4th place, there will be some inputs and some outputs. Okay. What are the inputs to the 4th place? So I'm going to add 2 numbers. I'm focusing right now on the 4th place. What are the inputs to the 4th place? I'm asking a question. And I'm getting no answers, so very good. All right, so here, this is an answer of my addition. Here's my 4th place. This is an output. And these are the inputs. When I'm in the position of the 4th place and adding numbers, I have the bit, the 4th place of A, that's one input. I have the 4th place of B, that's a second input. And I have the carry, whatever I carried from the 2's place, that's a third input. As far as the 4th place is concerned, the carry from the 2's place is an input. Does that make sense? This is where somebody brave says yes. Nobody is brave. Okay, thanks. So the inputs to the 4th place addition are the 4's bit of A. Let me make this some kind of silly list. The 4's bit of A, the 4's bit of B, and the carry from the 2's place. Those are the inputs of the 4th place. There were 3 of them. You can see them here. I have a number A, and it has a 4th place. I have a number B, and it has a 4th place. And I also have to add, along with them, any carry from my 2's place addition. So it is an input as far as this position is concerned. Then we're going to have the output of the fours place. One of them is going to be the sum of the answer. So the fours place of the sum, the fours place of the answer. That should say fours bit of, I'll say sum, like that. That's one of my outputs for the fours place. But I have another output, and that is the carry that's going to go to the eights place. And we saw that here. This came from this addition. So when we're adding in a given position, when we're adding binary numbers in a given position, we're going to have three inputs. That particular position for the first number, that particular position for the second number, and the carry from the previous position. And we're going to have two outputs. The answer, that same place for the answer, and the carry to the next higher place. Okay, so that's what we need.
I have a question.
Yes.
What if there is no carry?
It's 0.
Okay.
So there is a carry, it just happens to be 0.
Okay.
Thank you. Yeah, no, good question. So it's always going to be there, and in our binary world, it's 1 or 0. So in what you think of as I have a carry is a 1, and what you think is I'm not carrying is a 0. Okay. So now let's make a truth table. There are 3 inputs. That means that there are going to be 8 rows. And then I'm going to have these 3 inputs. So that's for inputs, I need 3 columns, and for outputs, I need 2 columns. And then I want some labels. So I'm going to have what, 9? I'm going to make a table here. And what do I want? I'm going to have 5 rows. I think that's what I want. I'm going to have 9 rows, 1 for headers, 8 for all the combinations, and 5 columns. Okay. So this is going to be A and B, and we're going to call this the carry in, and that's an input. And then I'm going to have the sum, and I'm going to have the carry out, and that's our name for the carry that goes to the next higher position. So this is the carry from the previous addition that's coming in as an input. This is the carry that's going to the next position. So this is an output. So we call them carry in. The carry in is an input, and carry out, that is the output. We're going to write down all our combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, and 1, 1, 1. And I went with the binary counting order here, but I could just as well have played the gray code order game, so long as I have all of them. If I have all of them, I have all of them. A truth table needs all the possibilities, except sometimes when we have those don't care things. But in this case, we do care. And so we just need all the combinations. I went with binary counting to get all my combinations, but I could have done gray code just as well. And if I add 0, 0, and 0, the sum is 0 and the carry is 0. And if I add 0, 0, and 1, the sum is 1 and the carry is 0. And if I add 0 and 1 and 0, the sum is 1 and the carry is 0. And if I add 0, 1, and 1, the sum is 0 and the carry is a 1. If I add 1 and 0 and 0, the sum is 1 and the carry is 0. If I add 1 and 0 and 1, the sum is 0 and the carry is a 1. If I add 1 and 1 and 0, that the sum is 0 and the carry is 1. And if I add 1 and 1 and 1, the sum is 1 and the carry is 1. I pause to say, do you want me to do it again? Do you want, it's just, I'm adding horizontally and I'm getting an answer and then possibly a carry. So 0 and 0 and 0 was 0 and I did not carry. 1 and 0 and 0 was a 1 and I did not carry. 1 and 1 and 0 was 0 and I carried. 1 and 1 and 1, I had a 1 and I carried. Is that okay? This is, I'm claiming this is the logic of addition of a particular position. This is just one position of the addition, say the 4's place, but that's just an example. Is this okay? So if you do this, if you figure out this logic, you're doing what's called a full adder. If you were to ignore the carry in and just have these two inputs, then you make what's called the half adder. So you can always add. So I'm adding, basically I'm adding 3 numbers. I'm adding A and B and any carry in. But what I can do is add 2 numbers and then get the answer to A and B and then add the carry in. So I can always add 2 numbers at a time and get an answer and then use my logic again. So I can build what's called a half adder and sort of use it twice, or I can build what we call the full adder. So in the lab and in the presentation, I go through the half adder before I go through the full adder. But I'm feeling anxious today. I just want to get to the real final answer, get to the full adder. Okay. So there are 2 outputs, and these are the inputs. So let's do this. Insert a row above, and merge these. Come on. Merge. These are inputs. And merge this. These are the outputs. Come on. Okay. Let me do some nice centering or something to make it look nice. Okay. So these 3 are inputs, those 2 are outputs. Okay. Now we would like to do this as when we build it, we want to be efficient and we want to build the simplest thing possible. So we will, now that I have it as in binary order, I will put it into sort of a more of a gray code order. And so what am I going to do there? So then I need maybe 6 by 6, maybe. Let's try it. So this is going to be, no, that was too many, but anyway, A and B, and the combinations are 0, 0, 0, 1, 1, 1, and 1, 0. That's a gray code order for A and B. I only changed from this row to this row. I only changed 1 bit. From this row to this row, I only changed 1 bit. And from this row to this row, I only changed 1 bit. And I have 0 and 1 and 3 and 2. I have all the A's and B's. Now I had too many columns here, sorry. Delete columns, okay. Now my C, my carry in, is going to go across the columns, and I could have a 0 carry in or a 1 carry in. So that this should look familiar as the 3-input gray code Karnaugh style truth table, right? We've usually done more complicated than this. We've usually done a 4-input Karnaugh table, but this is the 3-input. The carry inputs going across the top, the columns, and the A and B inputs are going down like this. Okay. And 0 and 0 and 0 is, let me do a mergey thing here. Mergey thing here. Come on. All right. And 0, 0, 0 is 0. And which one am I doing? I want to do, there are 2 outputs. So let me do the sum. I'm doing the sum output. So 0 and 0, 0 and 0, 0, 0 and 1 was a 1. 0, 1 and 0 is a 1. 0, 1 and 1 was a 0 in terms of summing. 1 and 1 and 0 is a 0. 1 and 1 and 1 is a 1. 1 and 0 is a 1. And 1 and 0 and 1 is a 0. Yes, no, or maybe. We know what we see it, we see what I'm doing, we don't see what I'm doing. I got 1, maybe 2 nodders who are saying they see it. Other people are hiding behind their computers or behind their names on screen. All right, well, nobody said they didn't understand. Okay, so this is the sum logic in a 3-input Karnaugh style truth table. And again, let's just look at, say, this input. This is the sum input when I'm adding 0 and 1 with no carry. So the answer will be a 1. Here's 0 and 1 when I do have a carry, so then the sum will be a 0. So this is the game. Now we set up the Karnaugh style truth table for the full adder. And why do we do a Karnaugh map? To ask if there's any simplification. And so the question is there any simplification? Here are our outputs in the Karnaugh style truth table. Are there any simplifications? There are no simplifications. She shakes her head no. I saw it. Nobody else saw it, but I saw it. There are no simplifications. This is, where do we get simplifications? When we have these groups, sometimes I call them groups, sometimes I call them blocks. When there are ones that are all next to each other. There are no ones next to each other. This guy's next to a 0, next to a 0. If I wrap, it's always 1 surrounded by 0s. I call it the checkerboard pattern. Where have you seen it before? Parity. So parity and addition, kind of the same thing. And there's no simplification. It's just grind it out. Oh, this one is A prime, B prime, C. And this one is A, B, C prime. And this guy is A, B prime, C prime. And this one is A, B, C. Now, it's not a simplification. It's not an actual simplification, but there is a thing that we can just write down and call this thing. Do you know what that is? Do you remember that? And I don't see any responses here. It's an excluded OR. So we could do, what was it? Let me write it down again. A prime, B prime, C plus A prime, B, C prime plus A, B prime, C prime plus A, B, C. Or we could just say that it was an excluded OR, a 3-input excluded OR. There's a symbol for excluded OR, but I'd have to find it in Word and I'll be tired. Okay. It's kind of like a plus with a circle around it. I'm just going to say it's an excluded OR, a 3-input excluded OR. That's not a simplification. It's just another way of writing it, because it's a combination. It comes up in parity, it comes up in addition, it comes up a lot. So they say, oh, instead of you grinding out all those primes and AND gates and OR gates, let's just smash it all into a 3-input excluded OR. If you've worked on lab 4, basically it's a subcircuit. The excluded OR is basically a subcircuit for this logic. It's not a true simplification. It's just sort of a hiding. It just sort of hides the things. Okay. So we know what the logic of summing in is, that the sum is this excluded OR. So we know we can completely know the logic of the sum output. Now we need the carry output. I'm going to switch this to the carry out, from the sum to the carry out, get rid of these. Okay, let's play the same game. When do I carry out? If I'm adding the numbers and I have 2 or 3. If it's 0, I don't have to carry. If it's 1, I don't have to carry. But if it's 2 or 3, then I need to carry. So I'm adding 0, 0, and 0. I don't carry. I'm adding 0, 0, and 1. I don't carry. I'm adding 0 and 1 and 0. I don't carry. I'm adding 0 and 1 and 1. I carry. I have 1 and 1. I have 1 and 1 already, so carry and carry. I have 1 and 0 and 0. I don't carry. I have 1 and 0 and 1. I carry. So here is the Karnaugh style truth table for a given position, for the carry out output of a given position in binary addition. So you need to show me some blocks. Identify for me some blocks. This third row. Okay, so there, that pair, the third row, is what? So when we identify the block, then we go back to the inputs and we say what changes and what doesn't change. So A changes within rows, but we're only in a row, so it can't change. Same thing for B, can't change, but the carry in changes. So I'm just going to call it a C, but when I'm done here. But the third row is A, B. A did not change and was a 1. B did not change and was a 1. Okay, that took care of this guy and this guy, but there's still 2 other ones we need to take care of. So tell me some other blocks. Tell me other blocks you see. Blocks are allowed to overlap. Third and fourth row, last column. These 2 guys, okay. Third and fourth row, last column. Okay. So we identify the group. Then we go over to the inputs and ask who stays the same and who changes. It's the last 2 rows. A is not changing, so I keep A. B is changing. I throw it out. C is not changing. C changes from columns. I'm only in 1 column. It can't change. It was a 1, so I keep it as C. Now I've taken care of that one. There's one more one we have to take care of. Try to put it in a block. Somebody help me. Okay, so second and third row. Last column. Okay. So now we're doing these two. After you identify the block, you figure out who changes and who stays the same with the inputs. In the second and third row, A changes, we throw it away. B does not change, and it's a 1, so we keep it as B. And we're only in column, the second column or the last column, and so the carry in is a 1, so that's a C. And now we've taken care of all the ones. And so we have AB plus AC plus BC. And we've talked about this once before. This was the majority rules logic. So one time we called it the majority rules because there were 3 people voting, and if there were 2 yes votes, they won. If there were 3 yes votes, obviously they won. But it's also the carry. So the same way the addition was the same as parity, this majority rules is the same as carry. That's not always true, but for 3 inputs, it's true. Okay. So now we have the logic of addition. If I built this, 3 inputs, there are 3 inputs, and here's the logic of the sum output, and here's the logic of the carry output, I would have what we call a full adder. So these 3 inputs with those 2 outputs build the logic that is a full adder. By a full adder, we mean it's responsible for the full addition of 1 position of our number. So I'm just going to draw. So let me do this. Snip. And I'm just going to snip some space here. And if I had I'm just going to draw a box. Somewhere in here in this box is hidden this logic of either the 3 put in excluded or the A primes and the B's and all that kind of stuff. And this logic, but I'm going to have A and B, and I'll call it C in. And then I have the sum, which I'm going to write as that, or it could just write an S for sum, but that's like the math symbol sigma for summation, and a carry out. If I had that, if I make that logic and then sort of make that logic into a subcircuit. So we know how to make these things. We know how to do this. This is just some sum of products expression. I could put this on the test, and you ought to be able to build it. Same thing down here. I can put this on the test. You should be able to build that. So if we build it and have these 3 inputs and those 2 outputs, this is the full adder.
What is the symbol on the top right?
This thing? That's a Greek sigma. You can call it an S just as well. You could do sigma or S. This is in mathematics, sigma is a standard symbol for adding stuff up. And that's what we're doing. We're adding stuff up. But if you wanted to just put an S for sum, that would be just as well. It's just a symbol, but it stands for the sum output. And let me copy that. I'll throw that over here. Okay, so now I have, that looks terrible. Make it smaller. It won't look so bad if it's smaller. Okay. This is responsible for one position. So this is like the 4's place. Now we want to start putting something together to have the 1's place and the 2's place and the 4's place and the 8's place and so on. We want to, this is the full logic of one position in the number. But it adds, 3 bits and gives you 2 answers, but we can put these together to make something that adds multiple bits. So that's what we'll do next. But any questions on this before I start putting more of these together? Okay, let me show you in over here. So in lab 5, I haven't posted lab 5. I'll try to remember to do that tonight. In the beginning of lab 5A, I have you build some of these. I think I have you build a half adder. That's even easier. And then maybe put 2 half adders together to make a full adder. But then this has where is it? So I want to be Miss Digital there. There it is. There's a full adder. So this has, let me start a new page, new circuit. There is in here under Miss Digital, the 01 miscellaneous digital, Miss Digital, there's a full adder. So they spell out the word sum. They don't use the sigma. So the C in is the carry in. They spell out the word carry for the carry out. There's A and B. So this, again, this is the, in that box is the logic. They're just hiding it all, but the in that box is the logic for one of the positions of our addition. So I'm going to grab another one. And I'm going to say, let's imagine U1 was the 1's place. And U2 is, so if this is the 1's place, this is the 2's place. Okay. So what am I going to do? I'm going to take the carry out of the 1's place and make it the carry in of the 2's place. All right. So let's put in some switches so we can control some things. I want some power. I want some DC power. I don't want another power. I want a ground. Okay. Throw you away. Now the carries sort of take care of themselves. The carry out of one of the additions becomes the carry in of the next addition. So they are inputs for a given position, but they're not inputs for I want to add 2 numbers. They're in terms of the full addition of, say, 2 4-bit numbers, the carries are internal to the process. But so we need, when we're making switches to control our inputs, we're going to have switches for A and B. but we're not going to have switches for the carries because the carry in of the twos place comes from the carry out of the ones place. So let me start making a switch here. There's switch. I like it. This switch. I'm going to have one. I'm going to flip it horizontally and copy it. I'm going to do like 2 bits. You have to do 4 bits because I'm mean. Okay. So I'm just making the 2 possibilities, the high and the low. Let me make this black. I like to make my grounds black. So, okay, each switch connects to a high and a low, so I'm controlling the inputs. Okay. And let me move this over a little bit. Okay. I'm going to call these the A's and these the B's. So this is going to be my ones place of A, my twos place of A. So this is my ones place of A goes into this is my ones place of A. This is my twos place of A, so that goes over to this guy. Then over here, I'm going to have the ones place of B. And over here, I'm going to have the twos place of B. Okay. Now I want to sort of display what's going on. And so I want some kind of display. And I could do probes, but I'm not going to. I'm going to do a hex display. So I was here in this indicator, this thing that I always think looks like an 8 or a scoreboard. And I'm going to go for the hex display. Not these crazy ones, but one of these. I'll go for blue. And this is going to display my A, and I'm going to display my B, and I'm going to display my sum. And the way these displays work is it's the ones place, the twos place, the fours place, the eights place. So this was the ones place of A, so there it is. This was the twos place of A, so there it is. Again, you're going to be responsible for a 4-bit number, but I'm lazy. And then this one is the B's. So those were my A's. I'm going to make my B's, I don't know, blue for B. All right. That makes sense. So here are my B's. This was my ones place of B. So that connects there. Here's my twos place of B. So I'm going to connect that there. And then here's my answer. And this is the ones place of my answer. And here's the twos place of my answer. Again, you have to do 4 bits, but I'm lazy. All right. So let me put.
For the 4 and 8 fourths and 8 bits, you need 2 more adders.
2 more adders, and for each, so you will have 2 more adders. You will have 4 switches to input A. You will have 4 switches to input B. So you're going to have 8 switches. You're going to have 4 full adders, and then all of these are going to be connected rather than 2 hanging loose like I have. Okay. So I'm going to put all these down for now. If I'm being more careful, I should make them not all controlled by space, but I'll control them just by clicking on them for now. Okay. So right now my number A is a 0, my number B is a 0, and I'm adding them and I'm getting a 0. I'm going to make my number A a 1, and 1 and 0 is a 1. And if I add B, 1 and 1 is 2. And let me do what? Let me add one more. And this is a 3 and a 1 is 0. That doesn't make sense, except 3 and 1 is 4, and therefore I need a 4's place for that to make sense. And I don't have a 4's place. That's your job. Okay. So again, I have the 1's place and the 2's place. You need the 4 and the 8. I have 2 switches for my A inputs. You're going to need 4 switches because you have to deal with a 4-bit number. I have 2 switches for B. You're going to need 4 switches. And then all of these will be connected. And again, this is the 1's place, the 2's place, the 4's place, the 8's place. One of the most common mistakes students make is they get the order of these displays backwards. It's the 1, 2, 4, 8. So it's the place is increasing as you go toward the left. Just the way the numbers are. So the lower number is this is, you know, if I wrote out a number, it would be the 1's place, the 2's place, the 4's place, the 8's place. So this display makes sense. But I just know people sort of connect like mad and don't pay attention. And often they get their displays backwards. Any questions? Again, you're just going to have to add 4's place and 8's place and 2 more switches and connect them to the A's and 2 more switches and connect them to the B and connect the display and connect the display and connect the displayed answer. And then I'm going to ask you annoying questions about when, like overflow, like when, if I add 2 4-bit numbers, when can I expect the answer to be wrong? Right now, I have 2-bit numbers, and I'm showing you a situation in which it's wrong. Because I'm adding 3 and 1, which gets me 4, and I can't express 4 in 2 bits. I need the 3rd bit to express a 4. So right now, in terms of 2-bit numbers, I'm displaying overflow. You'll have to tell me when you make your 4-bit number, when do you have overflow?
When you have 4 adders, you have to connect each carry out to the carry in, right?
Absolutely. Exactly. So you'd put another one here for the 4's place. You carry out of the 2 would become the carry in of the 4, and then you'd have the 8s, and the carry out of the 4 would become the carry in of the 8. And so this is what we're doing first, addition, and then we'll start to figure out how to make it into subtraction, but with not, you know, maybe just a few minutes to go. I'm not going to finish this because that's your job, and not quite enough time to talk about subtraction. So I'm probably just going to answer any questions people have, if they have questions they want sort of on the recording, and if not, I'll stop recording and hang out for people who have individual questions. Anybody have a question for the recording? No. All right. So I'm going to stop recording. Come on.